Hey guys, Mr. McKinney here, just going over how to find Riemann sums. Riemann sums are just a method of approximating or estimating the value of a definite integral. So Riemann sums are just a way to approximate the area that's underneath the curve and really between the curve and the x-axis. The problem that we're going to start out with today is this one. We're trying to find the value of this definite integral, the integral from 0 to 5 of negative 1/5 x squared plus 5 dx. So we're trying to find this area, except we can't use geometry because this is a parabolic curve. So it's not going to be a quarter circle or anything like that. If this was actually a quarter circle, we would be at a vertical tangent line over here, and we're not because this is a parabola. Now, if I take the area underneath a velocity curve, which is what this one is, the area underneath a velocity curve is going to give me the distance. So we're just going to find a way to estimate the distance traveled for the first 5 hours if this was my velocity curve. And essentially we're just going to use different Riemann sums, different ways to approximate this area that's underneath the curve. So as we go through our Riemann sums lesson, we're going to do 4 different Riemann sum methods: the left endpoint method, the right endpoint method, the midpoint method, and the trapezoid method. These first 3 methods are all rectangles. The last one is a trapezoid, so it's not a rectangle, but the first 3 are all rectangles. It's just a matter of how you draw the rectangles. You'll see left endpoint method as LRAM. You'll see right endpoint method as RRAM. This would be the left Riemann approximation method or the right Riemann approximation method, or the midpoint Riemann approximation method. You don't see it as MRAM as much. LRAM and RRAM will show up. So let's start with a left Riemann sum. Now essentially, no matter which method we're doing for these first 3, we're going to be drawing rectangles. So we've got our curve, and the question is, what is the area underneath that curve? And we're going to use rectangles to estimate it. Now for the left endpoint method, we're going to look at each interval, and on this problem we're going to do 6 subintervals. It will tell you how many intervals to use. So in this case, we're breaking up the distance from 0 to 5, because that's what our definite integral was covering, into 6 different subintervals. And in this case, we're going to start out making them equal subintervals. So if I take 6 and I divide it by, if I take 5 and divide it by 6, each of these intervals is going to have a width of 5/6. So we're going to split it up so that the x distance between each interval is 5/6. So pretend like my picture was drawn a little bit better. Now, for the left endpoint method, for each of these intervals, I'm going to look at the left side and use that value to draw a rectangle. So between 0 and 5/6, I'm going to take the point on the left and use that point to draw a rectangle. And then between this next interval, which will go from 5/6 up to 10/6, we're going to use the point that's on the left to draw a rectangle. And we're going to keep drawing these rectangles until we've drawn 6 rectangles. We're going to find the area of each rectangle and then add them up. And that will give us an estimation for the area underneath the curve. And by looking at the picture, you can tell that this is going to be an overestimate because each rectangle is a little bit bigger than the actual area we want to calculate. Now you'll see this table, which is just a way to organize our information. So by base, we're talking about the base of a rectangle. If we're saying that the area for a rectangle is base times height, the base is the distance along the bottom. So if we have 6 intervals going from 0 to 5, the base would be 5/6 for all of our intervals. Now the x value is which x value should we be using to draw our rectangle. So for a left sum, the first interval goes from 0 to 5/6. So the x value that I'm going to use is 0. The next subinterval is going to go from 5/6 to 10/6. For a left sum, I'm going to want to use 5/6, the one that's on the left. Then I'm going to use 10/6, and then this next point would be at 15/6, and then at 20/6, and then at 25/6. And then if I got to the last one, it would be at 36 which is 5. So I'm going to use the left point on each of these intervals. So 15/6, 26, and then 25/6. So for this first interval, I used the point that was on the left side, so 0. For the second interval, I'm going to use the point that's on the left side, so 5/6. Now I don't really want the x value. I want to know what the y value is that goes with it. So I'm going to use a calculator. I'm going to put y1 as -1/5 x squared plus 5. And then I'm going to plug in each of these x values to get the f of x value. So if I plugged in 0, I would get 5 for f of x. If I plug in 5/6, and again, I'm just going to do this on the calculator, I would get 4.86111, or 11 dot dot dot. I don't remember what this digit is. If I plug in 10/6, then I would get 4.444. And I could plug in each of these values into the original function, and I'll show you guys that on the next slide. The area is going to be the area of each rectangle, which again is just base times height. So I'm going to take the base, and I'm going to multiply it by the height. So for this first rectangle, we're saying that the base is 5/6, and the height is 5. So 5/6 times 5 would be 4.1667. For the next rectangle, the base is still 5/6. The height is now whatever f of 5/6 was. So I'm going to do 5/6 times this value. So the area of this second rectangle here is going to be 4.0509. For the third rectangle, the base is still 5/6. The height, I'm going to use the height on the left side. So I'm going to plug in 10/6 into my function. So I'm going to be doing 5/6 times 4.44444, which is going to give me 3.7037. And I'm going to use my calculator to fill the rest of these out. And then I'm going to add up all these values on the right side to get the total estimate for my Riemann sum. So this is if I use my calculator and filled everything out. So I now have an estimate for the area under the curve. And on my calculator, the estimate is going to be 18.634 when I add all these values up. And again, we can see from the picture that this is going to be an overestimate. So this was a left Riemann sum. We have a bunch of rectangles. At each point, we use the point on the left side of the interval to draw a rectangle. So I'm never going to use this point down here because that's on the right side of this last interval. So this point for this rectangle, this point for this rectangle, and so on. All right, let's move on to what a right endpoint method would do. So let's say I only had 5 subintervals. And I'm not going to go through the math over and over and over again because it ends up getting very tedious. So for a right endpoint method, the process is the same. Now in this one, we wanted 5 subintervals. So we're going to have 5 rectangles. I'll switch colors so you can see it a little bit better. So we've got our first rectangle, our second rectangle, our third rectangle, our fourth rectangle, and you can't really see it here, but our fifth rectangle is down here on the ground, or it's flat. At each of these intervals, I want to use the x value on the right side as the x value that I'm using to draw the rectangle. So I take f of 1, and I use that as the height of the first rectangle. And then f of 2 as the height of the second rectangle. So if I do a right endpoint method, I'm going to use a point and then draw the rectangle going to the left. I'm going to add up these areas, and if I did all the calculations like I did on that last one, I would end up getting 14. And we can see from this picture that on this curve, a right Riemann sum would be an underestimate because each of these rectangles is smaller than the actual area. The midpoint method, you just break it up into intervals again, in this case 5 intervals going from 0 to 5, so each interval has a width of 1. For the midpoint method, you don't use the point that's on either side. You take the midpoint of the x values. So halfway between 0 and 1 is 0.5. I'm going to find the f value that goes with that. So this would be like f of 0.5. And I'm going to draw the rectangle using that value. So again, I would take halfway between 1 and 2, which would be 1.5. find the value of the function at 1.5, and use that height to draw my rectangle. With a midpoint, you're not going to be able to tell whether it's an over or underestimate, because if you look, each of these rectangles has a little bit too much and a little bit not enough. A little bit too much and a little bit not enough. So it's impossible to tell from a midpoint Riemann sum whether it's an over or an underestimate. The most important thing to remember is that we're doing a midpoint of the x values. We're not taking our two y values and averaging them. That's what the trapezoid method does. So we're just taking the two x values, going halfway in between, and then finding the y value that corresponds with the midpoint. So it's the midpoint of the x values and then find the y value that corresponds there. The trapezoid method, so instead of drawing rectangles to make an estimate, we're going to draw trapezoids. Now the area for a trapezoid would be 1/2 times b1 times b2 times height. That's the way I learned it when I was a kid. You might see it like this, b1 plus b2 divided by 2 times the height. Now for this case, we're used to seeing trapezoids that look like this when we're growing up. These trapezoids have been rotated on their side. So here's a base, here's a base. Like b1 and b2 are on the sides. And the height of this trapezoid, this is really what we had been calling the base on other problems. So if I do a trapezoid method, instead of doing rectangles, we're going to use both endpoints and we're going to draw a trapezoid in between them. So instead of a rectangle, we'll have a trapezoid. Now, again, these trapezoids don't look like the trapezoids that you're used to from elementary school math or middle school math or whatever. But they're just trapezoids on their side. So the two parallel sides are going up and down here. In this case, the trapezoid method would be an underestimate because it's always underneath this curve. It's not always going to be an underestimate, but for this curve, it would be an underestimate. And again, we would just calculate the area of 5 different trapezoids. And I'm not going to go through all the math on that. We'll do an example with trapezoids later on. But if I did all the math, it would work out to be 16.5. Now, if you've already calculated a right Riemann sum and a left Riemann sum, the trapezoid sum is always going to be the average of those two. So that's just, if you're doing a problem where you have to do all 3 of those, once you know the first 2, you can just average those, and that'll give you the trapezoid sum. Okay, now let's look and see how we did with our different approximations. So if I just hit Math 9 on my calculator, it'll chop it up into thousands of different subintervals, and we'll get very close to the correct answer. So if I hit Math 9 and just type this into my calculator, I would have gotten 16.667. So if we look at my left Riemann sum, it was an overestimate. Also, we did that one with 6 intervals instead of 5. The right Riemann sum was an underestimate. Midpoint was a slight overestimate. The trapezoid was a slight underestimate. In general, midpoint and trapezoid will be better estimates than a left Riemann sum or a right Riemann sum. The smaller you chop the intervals, the better your answer is going to be. I don't know whether the calculator does a left or a right or a midpoint or a trapezoid. I do know that it does lots and lots and lots of intervals to the point that their answer gets very close to the correct answer. All right, I hope this was helpful. I know it was a little bit confusing, so watch the other videos, and hopefully that'll help clear things up. Good luck.